Good. Yeah, so we have seen this framework of stochastic interpolants, and now we are going to see a particular application of this framework to estimate free energy differences between different molecular configurations. Good. Yeah, this is based on some work that is available on the archive, and the link is there. This was a collaboration with several people. Yayun He, who is one of my PhD students, Yuan Kidu, Francisco Vargas, he was also a Cambridge PhD student. He's now working at this startup, Saria, that is using this flow matching to generate proteins and amino acids and antibodies. Joaquin Wang, Carla Gomez, and Eric van den Einden. Eric is one of the main contributors on this stochastic interpolants framework. And most of the work that I'm going to describe here was done by Yayun and Yuanqi, and they are the real contributors here. I'm going to start with some motivation and for the problem that we want to solve. We may have a drug-like molecule, like this one shown here. This could be a new molecule. And we maybe are a pharmaceutical company, and we are thinking, oh, should we fabricate this drug-like molecule or not? Should we focus maybe more? Maybe this is an initial candidate. We don't know if it's going to work or not, but should we really focus on it or not? And one of the things that you want to know is if this molecule will dissolve in water. It's going to be soluble in water or not. It's going to be happy surrounded by water molecules or not. If it's not happy surrounded by water molecules, when you take a pill with the molecule, most likely you won't absorb it. Okay? And then you don't want this type of molecules that are not soluble in water. And to know what's going to happen in the real world, you need to think about these possible states. You have a state where the molecule is surrounded by water molecules, or another state where the molecule is completely separated from the water molecules. Okay? And the question is, what's going to happen in the real world? What configuration is more likely to happen? And think that the probabilities of the 3D atomic configurations for the molecules are given by the Boltzmann distribution exponential minus the energy times some constants. We already saw that. So we can think about that. Let's go from now energies. We have energies. We are denoting the energies now by this letter U here. We have energies, and we have molecular configurations, which could be this axis here. The x-axis are the molecular configurations. And we want to know what's going to happen in the real setting. This would be 3D molecular configurations where the water molecule is surrounded by, the drug-like molecule is surrounded by water molecules. And these are 3D configurations where the two things are separated, okay? You have energies for those configurations of atoms, and then you're going to obtain corresponding probabilities by taking the exponential of minus those energies. And there are some normalization constants here. These are the log normalizers of the distributions. The whole question of what's going to happen in the real world is what configuration is more likely? Which one has higher probability? And that involves the probability mass under these curves. I want to, sorry, let me close this thing. I want to know what are these probability masses. I want to know the normalization constants of these probability distributions. Okay? And we are going to call the normalization constants, the log normalizers are called the free energies. There is a good reason for that. I'm not going to go into the details, but yeah, these are called free energies, and you want to estimate the free energy difference because that's going to tell you what's more likely to happen in the real world, okay? And the question is, how can we do this? One of the things that, for example, I mentioned that there is this state B. You have a state B where the molecule is completely separated from the water molecules. How do you get the energies of these configurations? So these energies, I mentioned that in the first talk yesterday, the energies are given by a physics-based model. Many times this could be a machine learning model itself. You could have a graph neural network. And when you say that the water molecule is the drug-like molecule is separated from the water molecules, what you could do is in your energy model, you switch off interactions between the atoms in the drug-like molecule and the water molecules. So it's like as if the two things, they don't see each other. It's like the same as, the probabilities would be the same as having this thing in vacuum separated from the water molecules. Okay? That's how you would actually evaluate these energies in practice. So you have an energy-based model. In the first state, there are interactions between the water molecules and the drug-like molecule. You put all of them inside of a box, for example, and there are interactions between them. And in the second state, the water molecules don't see the drug-like molecule. And you want to estimate the differences in normalization constants. How can you solve this problem? It turns out there is a state-of-the-art method for solving this problem. And this method is called M-bar. Who has heard about M-bar before? Has anyone heard about this? No? Okay, good. This is probably one of the most successful methods used by pharmaceutical companies in drug discovery. And it will allow you to estimate these free energy differences with high accuracy. It works as follows. We have the first distribution here is the probability for the first state, and then the second distribution here is the probability for the second state. And M-bar is going to create interpolating distributions. Okay? These interpolating distributions are going to be very similar to what we saw for annealed importance sampling. If you remember, in annealed importance sampling, we had two distributions, and we were doing some form of interpolation between them. Here we're going to do the same. I said that, for example, state B corresponds to the water molecules not seeing the drug-like molecule by switching off the interactions in the graph neural network. I could control how much I switch off the interactions. From 1, maybe a parameter set to 1, there are full interactions, and 0, there are no interactions. And I could smoothly interpolate now between the two states. I have now a series of distributions, one where there are interactions between the water molecules and the drug-like molecule, and another one where there are less, and then less interactions, and at the end, no interactions at all. I could generate samples from these distributions using Markov chain Monte Carlo methods. Okay? You could do that. I could have now samples from the first distribution here, for example. And I could have samples from the other distribution here as well, the second one, from P2, and so on. And I want to know, I want to estimate the normalization constants of all these distributions. The question is, how can you do that? It turns out you can do this very easily with samples, training a classifier, okay? And in particular, a generative classifier. This is kind of, goes to a bit the basics of machine learning. In machine learning, I don't know if anyone has heard this idea of discriminative classifiers and generative classifiers, okay? In a generative classifier, you have now a generative model for data points for each class, and then you make predictions using Bayes' rule. No? In a generative classifier, you will have probability of class A, probability of class B, and then the probability of Y being class A given X, for example, is going to be proportional to the probability of class A divided by the probability of class A plus probability of class B. Okay? This would be more or less the posterior, assuming that there are equal probabilities for each of the classes. Okay? So this would be what a generative classifier tells me. And I have now these densities. They are normalized because I cannot calculate the normalization constants. But the normalization constants, the only thing that they do is they scale the curves so that they integrate one. And what I can do is assume that the normalization constants are free parameters in my generative classifier. And I can try to classify the data. I can say, I have these samples, I have crosses and circles, but I don't know from which distribution they came from. Now, I have this sample, for example, is a cross, and I can calculate the probability that comes from distribution A or distribution 2. And obviously, this cross here is quite likely to come from distribution A. But then this another one here in the intersection of the two distributions is not that clear, okay? And the height of the curves is going to tell me the fraction of examples that I would expect at each location in the input space to belong to one category or the other. So the idea is that now I have a generative classifier. The free parameters in my generative classifier are the normalization constants of the densities. I can scale them up or down. And I want to perfectly classify the data using this generative classifier. I can maximize the likelihood to learn the normalization constants. This is something that is used actually quite a lot in machine learning. And you can show that if you have a perfect classifier, the perfect classifier is going to estimate the density ratio between the two categories. Okay? And that's what you are doing here. You will estimate the right density ratio, and that's going to be given when you have the right normalization constants. Okay? Any questions so far on this? No? We're going to see it more clearly with an example. I mean, with the formula and all the maths. So, sorry about this. The slide is just improvised a bit, but so we have data now. These are going to be n samples from each of the interpolating distributions. I have a total of, I have m interpolating distributions, and I have n samples for each one. And I can evaluate the energies now of all the distributions on all the samples. I assume that each sample here is sampled from one of these distributions, that it has its energy and its log normalizer. This is the variables that I tried to estimate. I'm going to assume the same prior probability for each category, so I have the same number of samples generated for each distribution. And then this is base rule. The posterior distribution of the nth sample belonging to the kth distribution is going to be the probability that that sample was generated from that distribution times the prior, and it's going to be proportional to that, and then I will have to normalize, and I get just the same formula that I have here. So then, this posterior predictive, or the predictive probabilities of my generative classifier is the ratio of the density of one distribution divided by the sum of the densities of all the other distributions. These are normalized at this stage. And I can calculate the log likelihood. I just have a product over data points, and then a product over possible categories of each data point. And I want to maximize the probability that the model gives to the right value. Yeah, there is some derivations here. You evaluate the likelihood, you calculate the gradient of the likelihood with respect to these log normalizers, and you can set the gradient of that to 0 and solve, and you will get this equation for the log normalizers, and it says the log normalizer for the distribution M depends on the log normalizers of the other distributions. So there is no analytic solution. It's a bit like logistic regression. In machine learning, you don't have like analytics maximum likelihood solution, but you can do numerical optimization, and you can start with some initial value for the log normalizers. Maybe they are all set to 0, and then I iterate using this formula, updating only all the log normalizers up to 1. I can only evaluate the right ratios. Okay, I cannot evaluate the exact normalizers. I can calculate the ratios, but that's enough. Okay, so I will fix one of the log normalizers to be 0, and then the other ones will have the right value with respect to the first log normalizer. The free energy difference in the end is just the differences between the first normalization constant, the normalization constant of the first distribution, the log normalizer of the first distribution, minus the log normalizer of the second. Okay, this method is called M-bar, and it's guaranteed to have minimum asymptotic variance, which is great. This is widely used, and it's one of the most useful methods to solve this problem. Any questions about M-bar? No?
Maybe one question?
Yes.
So you here, you're estimating with the previous method you're doing, or?
So
it's just to get normalizing constants. Is
Yes, we are interested in.
And then you've still got this interpolation issue.
Yeah. So far, I'm not using the stochastic interpolants for anything.
Yeah. Okay.
I'm going to use it now in a version of this problem. Right now, MBAR is the state of the art, and if you can do these interpolating distributions and sample from them, you just do this, and it's the best thing you can have, at least with the current methodology. We're going to go into a setting where you don't have interpolating distributions.
Okay.
And that's where the stochastic interpolants will be highly useful. Generating samples from the interpolating distributions can be expensive also. So maybe you only generate samples from the initial distribution and the final one, and you want to do something else and not use MBAR.
So the point of this is to get a minimum variance sampling method from your target distribution, starting from some initial one.
Our goal, it will be to estimate the difference in normalization constants without using MBAR.
Okay, fine, all right. Okay, so this is the baseline, and then you.
Yes, this would be like a baseline, or this would be like a ground truth. Yeah, good. So MBAR is great, but we may not have samples from intermediate distributions. And in this case, you just have now these distributions from the first state, PA, and from the second state, PB, and there is no overlap between them. If you run MBAR, you run into problems. Why is MBAR not going to work in this case? You could think, oh, let's do it with two distributions, even if there is no overlap. It's not going to work because you try to solve a classification problem. And you want to say you have samples from the probability from the distribution A and from the distribution B. What is the probability that the samples from A come from distribution B? 0, because there is no overlap. And then what is the probability that the samples from B come from A? 0. So then, it doesn't matter what log normalizer you choose, you always maximize the likelihood. Okay? So the likelihood is going to be insensitive to the log normalizer values. So you cannot solve the problem if you don't have overlap. You need some overlap so that you have to choose the right log normalizer for each distribution to have the right density ratio at the area where there is intersection between the samples. Okay? So we're going to see how to do this now without intermediate distributions, and of course we are going to use these stochastic interpolants. Okay? We're going to use now this notation. The normalized density is P tilde. The normalizing constant is Z. The free energy is just the log of minus the log of the normalization constant. And this would be the free energy difference. Okay? So now, we could say, let's try to do basic things. The first thing you could try to do is to do importance sampling. Obviously, importance sampling is not going to work great here because there is no overlap between the distributions, but you could try to do it. Importance sampling is basically defined as follows. You have the free energy difference here. Z2 is just this integral. And then I can multiply and divide by P tilde 1. And then get the log normalization constant here inside. And this is now the normalized version of P1. And here I have now the density ratio between a normalized distributions. So in the end, this is now minus the log. And I have here an expectation over samples of P1. And then I have here exponential of minus the energy difference. This is just importance sampling. And I could just replace this expectation with a Monte Carlo average. You could try to do this. The problem is that importance sampling, as I said, can have very high variance. In fact, the variance could be infinite if you are not careful. So this method is also called free energy perturbation. These are kind of same methods. They appear in machine learning and statistics. They appear also in chemistry and so on. And in chemistry, they use the free energy perturbation. But it's just importance sampling. So this doesn't work because you have high variance. You can do the two distribution version of MBAR. It's called BAR, which was actually the first method that was proposed. BAR is called Bennett's acceptance ratio. It's just MBAR applied to two distributions only. And it's the same thing. You start with a guess of the log normalization constant, which appears in this constant C. And then you get a new updated version of the log normalization constant, and then you iterate. It's an iterative method, the same thing as MBAR. The The equation is slightly different, but the solution is the same as the one that you get with M-bar. That's great, but we have mentioned that this doesn't work when there is no overlap between the distributions. You could do something called target free energy perturbation, and it's as simple as using a transformation of the data to have more support. All the stuff that we have seen, you can use it to solve these problems. You could use a normalizing flow, for example. Okay? And the idea is that you have your samples from one distribution, you map them, and you obtain new samples from another distribution, P1 prime, such that there is high overlap with the target. And then you can do important sampling or bar or other things. And you could use this flow matching, for example, to do this. Okay? We have seen on the flow matching, you could use that you have samples from P1 and P2, so you can train a flow that maps samples from P1 to have high overlap with the samples from P2. The problem is that you need the density of the transformed samples. Okay? You will need, if you want to do bar or M-bar or whatever, you will need the density of the transformed samples and up to a constant. And that's going to be problematic because you need to solve this integral. If you remember the formula that we had from the continuous normalizing flows, we had this formula, and then here we had this integral from 0 to t of the divergence of my vector field evaluated on xs. Okay? We had this formula, and this is expensive. You need to evaluate this divergence. You need to calculate the gradient of the output of a neural network for each of the outputs with respect to the corresponding input. And that's very expensive. And then you need to put that into an integral. So that's problematic. And that's not going to be scalable. Okay? In high-dimensional problems, for example, this is going to be too expensive to be done in practice. So what we propose here is a different way where you don't have to do this integral of the divergence that is expensive. Okay? And we are going to do it by doing the mapping, not with this deterministic flow, deterministic normalizing flow. We're going to use SDs to map between the two distributions. We're going to have forward. Let me write it here. We have a forward and a backward SDE. We are going to have an SDE that maps samples from P0 to P1, and then another SDE that maps samples from P1 to P0. We have seen the framework of stochastic interpolants, and you could design these SDEs. You are going to have now a vector field here, U, that, and then we are going to have here the score times the variance of that appears. This is the factor that appears in the Brownian motion in the SDE, is this one here. And then this is Brownian motion, and we have one that goes forward from x0 to x1, another one that goes backwards from x1 to x0. Okay? This U is the energy. I didn't write the, sorry, I'm not using the score, I'm using the gradient of the energy. The energy is minus the score. So, sorry, the gradient of the energy is the same as minus the score. So I just rewrote a little bit the equations, but it's the same thing. And then we have this U. U is this drift. This would be kind of the expected value of the gradient of the interpolant. Okay, we saw it in the previous lecture. U is the expected value given xt of the gradient of the interpolant. And you could think of this as a control term that is guaranteeing that the marginal distribution has the right energy. Okay, these are the energies of at the different time values, and now these SDs are going to be mapping from one distribution to the other. Okay, the important thing is that this framework based on SDEs allows us to calculate the free energy difference without having to use this integral of the divergence, and we are going to see next how to do that. Okay. Some intuition of what's going on. maybe some of you are familiar with Langevin dynamics. Have you heard about Langevin dynamics? Some people? No? Okay. The key thing in Langevin dynamics is that imagine that this energy, U, is, so for example, in Langevin dynamics, you could have that dxt could be equal to, for example, minus sigma squared, the gradient of u t xt dt plus sigma square root of 2 d of the Brownian motion. Okay? And now, sorry, this one it doesn't depend on t. Okay? So this is just the energy. Okay, Langevin dynamics is basically a stochastic differential equation like this, where you have this these constants here, some sigma squared, and then there is like a square root of 2 here. And the key thing is that this SD is guaranteed to sample from a distribution with this energy. Okay? And this is quite commonly used in many areas. And the key thing is that this looks like a Langevin dynamics SD. The only thing is that the energy is changing as a function of the time. And this means that if you run this thing and the U is fixed, you are guaranteed to sample from a distribution with energy U. Okay? But here the energy is changing. And this means that as you are simulating your SD forward, you are trying to sample from the energy U, but this energy U is changing as a function of time, so you never really catch up. And actually, if you run this SD without the U term, this UT, you won't sample from the right distribution. This term UT, you could imagine of it as being a control term, ensuring that your samples have the right energies. Yes?
Is the variance also key?
I think it doesn't matter, no. This sigma can be whatever, and it will sample from the right distribution. Okay. Yes. It's the same as in the stochastic interpolants. In the stochastic interpolants, the sigma can be anything. You could make it larger or smaller. You always sample from the right distribution at time 1.
So like, just to understand, so are there two separate Langevin dynamics, one that started from distribution A that you let run, and then one started from B which you let run, but obviously backwards in time. Is that correct?
Yes.
Okay. But it's not a single one that starts from A and then ends up at B at the moment. Is that correct?
Yeah, it's not a single one. There are two.
Okay, fine.
And it's important that you have two. It's not exactly Langevin dynamics because it's like an SD kind of similar. Yes.
And then you might couple them somehow. They might.
Yeah, we're not really coupling them. We're going to see now what we do with them. But yes, good. Any other questions so far? No? Good. So it's the same plot that we saw before. You're mapping now between the two distributions with the SDEs. And that looks fine. It's kind of similar to what we could do with the continuous normalizing flow that is deterministic and it follows an ODE. But the key thing is that now we can calculate the free energy difference without having to calculate divergences, okay? And solving this integral of the divergence. And the idea is as follows. You are going to discretize the SDs. So you take some subset of points in the unit interval. These are time points at which you are going to be sampling from the SD model, and you discretize it in the sense that now you take a finite difference in values in the process, and you have this delta t. So instead of the differentials here, so we had this differential, this will be the difference between xt at different time values, and then this dt is going to be now the delta t, and here the delta t as well, and here we are going to have now Gaussian noise with variance delta t, okay? So that's what we have here. Now we have a discretized version of the forward SDE, and we're going to have a discretized version of the backwards SDE, okay? And sampling from this is very easy. It's just sampling from Gaussians. You evaluate the drift term that is deterministic, and then you add Gaussian noise. And these sigmas, these eta variables, they are just the standard Gaussian variables. Okay. Now, if I can sample from these SD models, I can estimate the difference in normalization constant, or the ratio between normalizing constants, using importance sampling. Okay, I'm going to do now importance sampling not between samples from the distributions. I'm going to do importance sampling using the trajectories of the SDs. Okay, and this is what I have here. I have now in the denominator, I have the unnormalized density for the starting point in my forward SDE, and then I am sampling from Gaussians afterwards, and that's why I have these extra terms here. This would be the probability that my discretized SDE gives to the data points that I obtained by sampling from that model. No? And now, in the numerator, I have the probability that the backwards SDE would give to those points. And that probability is the normalized distribution at the end of the discretized sample times the probability that the backward model gives to all those samples. Okay? It's the product of all these Gaussians. These Gaussians are given just by this Gaussian noise that appears here. Okay? So the probability of this Gaussian on xt minus 1 is just a Gaussian with mean this. This would be the mean of that Gaussian, and the variance is going to be this. Okay? And the same for the other model. So now I have these density ratios for the discretized SDEs, and if I calculate the expected value of that, it's going to be the difference between the normalization constants, and those are exactly the same differences in normalization constants of the original distributions. Okay? Because if this thing is normalized, then this thing integrates 1, and this thing is if the initial distribution is normalized, this thing also integrates 1. So if I calculate this expectation, I have the right ratio between normalizing constants. This expectation is with respect to the samples of the forward SD. This would be x forward. Okay? I can do the same the other way with respect to samples from the backward SDE, and then I have here backwards. And the only thing is that the ratio is the opposite. Now here I am sampling from the backward model, and then evaluating the probability of the generated samples with respect to the forward model. Okay? And then I take the log, or minus the log. It's just the same free energy difference. It's just important sampling on SDE trajectories. And obviously, this is unbiased. Okay? It doesn't matter. My SD models could have errors. I could have had some mistakes in the estimation of the, I don't know, if I am estimating these energies and these drifts, I could have mistakes there. It doesn't matter. This is still unbiased. Good. This is going to reduce variance, but it's still important sampling, and it can have high variance. So you need to be careful with this. What you can do next is to improve things. And in the same way that M-bar is better, M-bar and bar are better than important sampling, we can use a bar-style method to estimate now the ratio between normalization constants. So instead of doing important sampling, now on these trajectories of the SDEs, you can do bar on those trajectories. Okay? And it's the same thing as what we did before. So if you think about what we did before with bar, you have some initial guess for the free energy difference, C. You initialize it to that guess, and then you update C to be the value given by this expression, and you iterate, where G is this function. So we can do exactly the same, but now we operate on the trajectories of the SDs. And this is going to reduce variance quite a lot. And That's going to make this method work quite a lot. The only thing that we need is some overlap between SDE trajectories. If we have overlap between SDE trajectories, even if there is not so much overlap between the initial and the final distribution, this thing is going to work. Good. Any questions so far on this? Yes?
Feels a little bit unconvincing that, so the equation at the top there just felt a little bit strange, because, so essentially, if I understand this right, you've got like an Euler-Maruyama
Yes.
discretization of the
Yes.
SDE.
Yes.
So there's some error involved in that.
There will be some error. Yes,
Yeah.
that's right.
And so, so it feels like that error perhaps should be the same in the forward case and the backward case for this to be true.
Yeah, it could be that you have similar errors in these cases. Yeah.
But why should those be strictly equal?
Because these are exact expectations. So these are, imagine that I take an infinite number of samples.
Oh,
then
okay.
it will be fine.
I see. Right. Yeah.
Yes, if you use a Monte Carlo approximation, then that's not going to be the case.
Okay.
Good, so yeah, we can do bar now operating on the trajectories of the SDs instead of on the samples directly. And that's going to reduce variance. And if we have these SDs well trained, and in principle we do like a very large number of steps, these ratios will be the same, okay? And we wouldn't have like high variance. Now, how do we learn these SDs? We have seen already all this in the previous talk, so I don't need to give a lot of details on this. But yeah, the idea is that to learn the SDs, you will use this framework of the stochastic interpolants. You get this interpolant value, xt. You obtain it by doing a linear combination of the samples from one distribution and the other, and you add a little bit of Gaussian noise. Then you estimate the drift as the conditional expectation of the derivative of the interpolant with respect to the time value, and then the score, or the derivative of the energy, is just done by estimating the epsilons or the Gaussian noise that is used to generate the interpolant. You have two losses now, one to regress on the drift, and on the drift model, and another one to regress using the score model. Okay, and you can train them from data. So it's more or less what we already said. So now some examples of how this works in practice. We have this Gaussian mixture model. These are some problems. This is also, okay, the problem is still quite challenging, and some of these problems, they are not really that high dimensional, but they are way better than previous methods. So it's some advancement here. So this is a problem with mixtures of Gaussians, with 16 modes, one of the mixtures, and the other one with 14 modes. They are like two different distributions. These are normalized, and we know that the log, the free energy difference is going to be 0, because both have the same normalization constants. We use another problem, which is a Leonard-Jones system. In this case, you have particles in a box, for example, and they're going to interact according to some potential energy given by a Leonard-Jones potential. And we have two systems, one where the particles interact with the Leonard-Jones potentials, and the other one where the particles don't interact with each other. Another problem is with this dipeptide that we saw in the first talk that I gave. There is this small amino acid. There was this histogram of the angle values that the 3D configurations of the molecule can take, okay? And we had several modes there. We can think that one of these modes corresponds to one of the states, okay? We say when this angle phi is between this value and this value, this is one of these states. And the other state corresponds to other values of this angle. This will tell us what is more likely to happen in the real world. Is this molecule going to have this particular dihedral angle taking this value or larger values? Okay? We want to kind of calculate the probability mass for each of these configurations. And this is this problem with two metastable states. And then we have another problem with an dipeptide, where the molecule is in vacuum or where it is supposed to be surrounded by other molecules like water. This is an implicit model, so there are no real water molecules there, but there is like the energy changes, assuming that there is some solvent around the molecule. Okay? And we can then compare with other methods. We compare here with M-bar, which is our reference. In this case, we use samples from intermediate distributions, and given enough samples, this will give us enough samples and enough intermediate distributions, this will give us the right value. In the first case, we don't even need to run M-bar. We know that the free energy difference is 0. This is for the mixture of Gaussians model. We have here results for the Leonard-Jones problem. We have 55 particles, 79, 1 and 28. Each particle has three coordinates, 3 spatial coordinates, so this would be the dimensionality of the problem. And we see what M-bar was giving us here, in this case, and in this case. And then we have here some baselines. This is the method based on flow matching, where you need to calculate this integral of the divergence. That method is not going to work in high-dimensional problems. And here we were not able to run that method. It's too expensive. We have another baseline. This is called neural thermodynamic integration. The idea here is to feed a diffusion model and to use the length diffusion to estimate the energies. I won't go into the details of that method, but it's another baseline that has been proposed recently. And here we include results for our method, and we see that we obtain results that are closer to the ground truth than for the other baselines. And this is for the alanine dipeptide. The alanine dipeptide problems, the dimension here is about 60 or so, and we get similar values to values that are close to the ground truth. We improve over, for example, yeah, I think in this case the differences are less clear between the different methods. But yeah, this is more or less the results here. We can see the gains of the improved estimator using this bar approach, and we see that we have way less variance. So this is the minimum variance estimator that uses the bar approach and if you do important sampling, you will get results like these red curves, okay? While the blue one converges here way faster, and here also converges way faster. So using this bar approach is way more effective than doing important sampling, which is, I mean, it's what we would expect. So to conclude, here I have presented this FEAT method, free energy estimator, with the adaptive transport. It calculates the free energy differences between samples only from initial and final state. It doesn't need samples from intermediate distributions. It uses this stochastic interpolant framework to learn SDEs that are going to be mapping between the two distributions. It avoids calculating changes in density, so we don't need to calculate the integral of the divergence, which is expensive, and we use this bar-like estimator that has minimum variance, and we have seen that it performs better than other baselines. Obviously, there are limitations in this method. You will need to train your SDE models, okay, and that requires some cost. The advantage of training the SDE models obviously would be generalization. Maybe you can train SDE models across several problems, and then you get a new instance of the problem, and then you can use the pre-trained models. That would be the ideal case. We are thinking about doing something like that to assess the capacity of this method to generalize in those settings. In high dimensions, you may still struggle, because the forward and backward SDE models are not going to be perfect, and they're going to be making different probabilistic predictions, and this means that when you calculate their ratio here, this density ratio between the forward and the backward model, you will still have a high variance in high dimensions. So you need to be careful with that. But I mean, we are still better than previous baselines, which is good. Yeah, this result also has not been published yet. So it's this is unpublished results. And yeah, that's all I wanted to tell you. So I'm happy to still answer any questions. I think we still have quite a lot of time left. So yeah. Yeah, it's harder to say. So, so what happens is that you have the energies. Let me see where I have this. Yeah, so you have these energies, and you could say, yeah, maybe in a particular configuration you get these energy values. In another configuration you get maybe these other energy values. It's hard to know what's going to happen because, I mean, you will be only evaluating the energy at a particular point. And what you care more is about the whole range of possibilities here. So you need to solve the integral. You need to integrate more than just evaluating the energy. A very simple way to try to approximate this, I don't know if you know about this Laplace approximation. So you could think about using the Laplace approximation here. You could try to optimize the energies to find a configuration with low energy, and then use the curvature and just the height of the curve there. And that could be like something very cheap and very easy to do. The problem is that it's not accurate. And people don't use the Laplace approximation. So my understanding is they don't use the Laplace approximation because these distributions are not close to Gaussian, and the Laplace thing will not be good enough. In some cases, they do use the Laplace approximation, and it may be fine. But ideally, if you want to be fully accurate, you need something like M-bar or more general.
Okay, that's fair. But isn't it still the case that you just get about one integral being larger than the other, rather than actually knowing the difference? Or am I missing something? Just basic.
Can you repeat the question? What do you mean by one integral? Or?
So if I understand correctly, like generally speaking, chemicals will move from a higher energy configuration, like sets of configurations, to lower energy sets of configurations. If you just know the average behavior, doesn't that already tell you whether it will be soluble or not?
It may work in some problems. I mean, people do this integrated Laplace thing. So you could try to do like a mixture of Laplace, and that will be more accurate. And maybe some problems that's fine. In others, it may not be. My impression is that the Gaussian thing might not be that accurate. The other thing is that these things, they could be multimodal. We saw it in the alanine dipeptide, you have multiple modes. Then the Gaussian with a Laplace, it might not be that accurate. And you may need like this type of things that are more general.
Can I? Yeah.
You spoke about the free energy difference that involves the energy and the entropy. Is the entropy information coming from the probability distribution?
I'm not an expert in this area, to be honest. Yeah, I mean, you can look at there is like where is this thing? I mean, you have this normalization constant, and yeah, it's related to the entropy. And I read about this recently, but I'm not an expert on that. And there's a connection with the entropy. I won't be able to tell you about it. I think you can find it in normal references. They will tell you the connections between this free energy and the entropy. Yes.
Any other questions? I maybe had two quick questions. One,
yeah.
I'm going to max out my chemistry knowledge pretty quick, but my understanding is that when pharma companies care about solubility, it's not necessarily like an oil and water thing, but it's more like the tablet, it'll be like a crystal, and then the tablet, the form of the crystal and the tablet matters. So you could take a molecule that's soluble in one polyform, it's soluble as a tablet, but another polymorph is, it could have another polymorph, and then it wouldn't be soluble. If you see what I mean. And so I was wondering if that is something that one could account for within these frameworks. And that maxed out my chemistry knowledge. If that's maxed out yours, no problem.
Yeah, I think it will probably matter. I think finding this crystal structure is important also. And that's like a challenging problem. I think you can use similar techniques.
Yeah, there's still energy functions and all the rest of it. So
the problem is that it can be quite more complicated if you want to look into the crystal.
And a second question, which is probably a bit more related to your interest, so maybe like you can get these sort of estimates. I guess you could computationally get estimates between your kind of A and B distributions potentially It's just they're kind of expensive physics calculations. So do you think there could be like a Bayes optimization approach where you try to say, I've got this good estimate of my SDE, but I haven't explored this part of the space?
Yeah.
You could then, you know, start to use some of those Monte Carlo methods you're discussing, or maybe some Bayesian Bayes approaches.
Yeah, I think that would be, I mean, that would be great. For example, this just, you have some data and you train models and that's it. Obviously, your models will make errors. No, you will have, when this is going to fail or going to struggle, it's going to struggle when these ratios here have high variance.
Yeah.
And they will have high variance when the forward model and the backward model don't agree much with each other. So you could imagine that maybe you train these models and then you have maybe areas where there is low agreement between the models and you could try to do things to correct those. And thing that you could do is an important sampling.
Yeah.
I mean, this is still important sampling.
Yeah.
No? So you could think of doing an important sampling to reduce the disagreement between the models. And you could maybe collect more data and maybe train the models there and do some form of active learning or
because you don't need to go to a wet lab to do these things. You could just computationally, it just takes time, that's it, you know, so you can kind of get that, put this into the loop. And
I think it's, people haven't tried that, and it's probably expensive to do it, but
sure.
I think, there could be many ways to do those things.
Okay, great.
Good.
All right, perfect. Well, thank you so
Thank
much,
you.
Miguel. Thank you.